Anyway, without further ado, please join me in welcoming Steve. He's going to talk about creating Schrödinger cats with microwave photons. Welcome, Steve.
Okay, thanks very much, Leo. And I'm extremely grateful for Leo to doing all the work for the Boulder Summer School. And he does a tremendous job. So I gave the qubit seminar yesterday. There'll be a sort of 10% overlap, and some of the initial slides will be similar. But I'm going to try to go slowly and explain to people not working in this field how you control the quantum state of a harmonic oscillator and do things like this is sort of position, this is momentum, and you make a Schrödinger cat in which the oscillator is in both here and here in some funny sense at the same time. And it's not a mixture, it's a coherent superposition because of these, what we call the whiskers on the cat. And this is going to be made out of, you can do this with mechanical oscillators and trapped ion systems. Some people here think about that. But we're going to use electromagnetic oscillators in the microwave regime. And, I hope the students will be comfortable interrupting me and saying, I didn't understand what you just said. Can you clarify? Okay, so don't be shy. All right, so something's not quite working yet. Oh, I think I have to put the cursor here. That's what it is. Okay. All right, so what's quantum electrodynamics all about? It's about the coupling of the quantized electromagnetic field to atoms and electrons. And the vacuum, instead of being empty, is full of zero-point fluctuations of both electric and magnetic fields. And particularly those electric fields, primarily, have interesting effects. So, for example, you learn about the stationary states of the hydrogen atom. They're not actually stationary. The 2p state can fall down to the 1s state because it's being jostled by the vacuum fluctuations of the electric field. And it falls down in about 1.5 nanoseconds, pretty fast. These vacuum fluctuations cause the electron to emit and quickly reabsorb photons, and that changes the effective mass of renormalizes the mass of the electron. It causes this Lamb shift that lifts the degeneracy that you first learned about when you derived the spectrum of hydrogen. Those are naively degenerate, but not in the presence of vacuum fluctuations. And the whole story of cavity quantum electrodynamics is to try to change the spectrum of the vacuum fluctuations, which are occurring at all frequencies from 1 hertz to gamma ray frequencies. And by filtering out or enhancing or filtering out those fluctuations using resonators. So it can be an optical resonator, which is just a Fabry-Perot cavity with 2 highly reflecting mirrors. Or for us, it's going to be an aluminum box cooled down near absolute zero. So it's superconducting, and microwave photons see essentially perfect reflectivity in all directions, and photons stay trapped inside. And so, but now the electromagnetic modes are not continuous, they're discrete. You have certain, integer numbers of wavelengths or half wavelengths that fit in these boxes. And you have a little bit of coupling to the outside, and so the vacuum fluctuation spectrum is different, and it can affect the Lamb shift, it can affect the lifetime. In particular, if you arrange to put either a natural atom or a synthetic atom, a superconducting qubit, inside one of these boxes, and the cavity does not have a mode at the frequency that the qubit wants to emit a photon, then that emission is highly suppressed by what's called the Purcell effect. And for us, our synthetic atoms will spontaneously emit a microwave photon, not in a nanosecond, but in about 100 nanoseconds. And putting it inside a box where there are no modes for it to emit into will increase the lifetime by a factor of 1,000. Not by infinity, unfortunately, because there's pieces of dirt that will absorb at almost any frequency. But still, we live by that factor of 1,000 when we're trying to build quantum computers with qubits that have long lifetimes. Okay. All right. This is just not working. All right. So for us, we have these synthetic atoms. They're little superconducting antenna, about 1 millimeter in size, made out of thin film aluminum. The two halves are loaded with a large inductor. Those of you who maybe have used radio transmitters in your car and you don't want to have a very tall antenna, you wind it up in a coil, load some inductance on it. That inductor here is a Josephson junction. And so it's a centimeter scale wave that resonates in a millimeter sized object because of that inductive loading. And it's in a cavity which has also some centimeter scale gigahertz frequency photon resonances. Okay, so here's a picture of one half of such a cavity, two pieces of aircraft aluminum, 6061, glued together with some indium O-ring to make it superconducting. There's a piece of sapphire here, and there's the millimeter scale little piece of aluminum evaporated on the highly insulating low loss sapphire. And the excitations of this qubit, because it's superconducting, are pairs of electrons, Cooper pairs, traveling frictionlessly, sloshing back and forth, and producing excitations just like an antenna that you drive with a signal generator. And this is a slightly nonlinear inductor, this Josephson tunnel junction. And so it produces not a harmonic oscillator like an LC circuit, but a slightly anharmonic spectrum, which is simpler than hydrogen. It doesn't have fine structure. It's just a weakly anharmonic oscillator with a frequency of 5 to 10 gigahertz. And the next excitation frequency is maybe 1% less than the first. And there are 0-point fluctuations of this oscillator, the charge going back and forth, and they correspond to 2 or 3 Cooper pairs moving about a millimeter. And for the atomic physicists in the room, that gives us a transition dipole moment of 10 million dBi, or several 10 millions of dBi. DBi is I don't know, is it 1 electron moving a Bohr radius, roughly, or maybe exactly? And so this is a huge dipole moment that allows you to couple to the 0-point fluctuations of the electric field in the cavity and allows the atom to exchange energy with the photon field about 100 million times per second. That's what this vacuum-Rabi coupling is. So there's, I'm going to treat this oscillator, I'm going to ignore the higher levels because they operate with different transition frequencies. Just focus on the lowest 2 and pretend that's a 2-level system described by, like a spin a half or a qubit. By the transition between them is a Pauli X matrix, and here's the electric field operator. creates and destroys photons in the cavity. And so the vacuum, the 0-point fluctuations of the electric field times this dipole moment gives this G of 100 megahertz. Okay, questions about that? So I remember trying to calculate that the first time, and like, what is the vacuum electric field and all these things, and came out to be, when I finally got the units right, 100 megahertz, and I thought, wow, maybe this is big enough that we can see it. And so now, rather than making the qubit have the same frequency of the cavity, I'm going to make it different. I'm going to detune it by some distance delta above the cavity frequency, let's say. It doesn't matter whether it's above or below, but let's say it's above. Okay? So photons in the cavity cannot be absorbed by the qubit. So it's like a piece of transparent glass. You can see through glass because the excitation gap is bigger than the energy of visible photons, so they can't be absorbed. But glass has an index of refraction, right? So you can virtually absorb the photon, not quite making it up there, and then quickly jump back. And that sort of second-order process leads to a frequency shift of the photon, or of the resonance frequency of the cavity, it pushing it down. Okay, so that's the same thing when you put glass in a resonator. If the qubit is in the excited state, things work the other way around. I'm in the excited state. I'd like to emit a photon, and I'm stimulated to emit it if photons come by, right? As Einstein taught us, there's stimulated emission. But I'm stimulated to emit at this frequency, doesn't quite reach 0, and so I quickly go back. And that also produces a second-order energy shift, but now the energy denominator has changed sign, and the shift is in the other direction. Okay? So it's like a piece of glass whose index depends on whether the qubit's in the ground state or the excited state. And so the frequency of the resonator now depends on the state of the qubit. Okay? So this dipole coupling, which had a sigma x in it, when you go to second-order perturbation theory, you end up with a sigma z a dagger a. And this dispersive shift is given by the vacuum-Rabi coupling squared and the detuning. Okay? Is that clear? So, so as I said, this is like when you put the qubit inside the cavity, it's like putting a piece of glass in a Fabry-Perot optical cavity. It effectively increases the optical length of the cavity and therefore changes the resonance. And the thickness of the glass or the size of the index of refraction depends on whether the qubit is in 0 or 1. So, and the glass is transparent because it doesn't actually absorb the photons. Okay? So that's how you can, so now that's the dispersive interaction between the qubit and the cavity causes the cavity frequency to depend on the state of the qubit. And that's described by this term we had before. And so if the qubit is typically chi is negative, for us, and if the qubit is in 0, the cavity frequency will be down here. If the qubit is in 1, it'll be way up here. And that can, yeah?
Can you say something about the imaginary part? How the order of magnitude?
Well, so if this is a 5 gigahertz cavity and a 6 gigahertz qubit, the absorptive part is, if you're 2,000 line widths off resonance, the absorptive part is. Yeah. So it's 2,000 line widths away, so it's 1 over 4 million or something. Yeah. Yeah. So it's very strong dispersive coupling. All right. So we can use that to measure the state of the qubit because we just shine microwaves on the cavity and see whether it resonates here or here. And they're not absorbed, they just bounce off, and they have a phase shift that depends on this, whether the resonance is here or here. Let's say if I drive here, I get a pi phase shift if the qubit is in 1, and because I'm on resonance, and if it's in 0, I'm way off resonance, and I get either 0 or 2 pi phase shift, which is indistinguishable. And then I measure that phase shift of the microwaves that bounce off. Okay, and then as you can rearrange the parentheses here and say that, well, actually the same dispersive coupling tells us that the coefficient of sigma z, which is like how much energy it takes to excite the qubit, now changes depending on A dagger A. That's the number of photons in the resonator, and it shifts 2 chi for each photon that you add. That's the light shift. So I can use that to measure the number of photons in the resonator. It's like a non-destructive photomultiplier with number resolving capabilities. So here's the cavity, the resonator in the vacuum state, and there are no photons in there. As I sweep the frequency trying to excite not the cavity but the qubit, and then measure whether the qubit got excited, it just has one peak there. If there's a superposition of 0, 1, 2, 3, 4, 5 photons in the cavity, I'll see a peak here, here, and here, because photons are particles. The energy of the light shift is quantized. And so this allows one to do very sensitive measurements of by counting photons, and people are using this to search for dark matter axion particles, actually. Okay, so what I want to try to understand now is how to use these tools in which you can measure the qubit using the cavity and measure the cavity using the qubit to control both objects and measure both objects. And the control task is, I want to, you tell me what arbitrary superposition of 0 photons, 1 photon, 2 photons, 3 photons you would like me to make in the cavity, and then I have to find a recipe to do that. Okay? And it turns out that if you have classical drives on a qubit, you can universally control it. You can rotate it around anywhere on the block sphere, and it's fine. But for an oscillator with a classical drive, you can't actually do anything except displace the oscillator in position or momentum, creating so-called coherent states. So we need to have this auxiliary superconducting qubit, this synthetic atom, this 2-level system, to let us have control of the oscillator using this dispersive coupling. And so we're going to steal some ideas from nuclear magnetic resonance, where you learn how to control nuclear spins and turn them and so forth, and also ideas from trapped ion experiments to try to control our, in trapped ion experiments, you're trying to control the mechanical oscillators. Here we're trying to control these electromagnetic oscillators. And we also added some new ideas using this dispersive coupling, which is natively available for us and absent in ion traps. So, so when you study the quantization of the electromagnetic field, it's all very confusing because you're using second quantization, and x is the position in space, not the coordinate of some oscillator. And so I'm going to very simplify things by saying among the many modes in this cavity, I'm going to just focus on the fundamental mode because it's close to the qubit frequency. It's a harmonic oscillator. and it has a coordinate, which is actually the electric field, let's say, at the center, and a momentum, which is the magnetic field at that point. But I'm just going to, think of by a mechanical analog. I'm going to use first quantization to describe this single harmonic oscillator. And we'll recall that the wave function, the first quantization picture of the oscillator in the ground state, is just a Gaussian. You want the position to be a little uncertain so that the momentum uncertainty is not too large, right? And then the first excited state is x times the Gaussian, and so forth. So this is very familiar. And it's exactly, this is really just, say, psi naught of electric field at the center versus the E. That's the same thing for this electromagnetic oscillator. Okay, so the wave function is a Gaussian. Its square tells me the probability of finding a particular position, a particular electric field in the vacuum state at this point. And the 0-point fluctuations are given by this parameter sigma. And how big it is pretty straightforward to calculate from the formula for the electromagnetic energy density in a box. E squared plus b squared has to end up being a half of h bar omega, the 0-point energy. Okay, so it's convenient to take, instead of talking just about wave functions as a function of the position, that is to say the electric field, not the physical position here, but the electric field at this point is the oscillator coordinate. It's convenient to talk in a phase-space picture in which you try to talk about position and momentum at the same time. But of course, they don't commute with each other, and the uncertainty principle says you can't localize to a particular point here, so there's sort of a Gaussian blob in this minimum uncertainty packet. But it's a convenient sort of semi-classical way of looking at things. Okay, so what's a coherent state? It's just a state whose wave function has been displaced. It's the vacuum, but you moved it over to some position x or some momentum p. And so it's a displaced Gaussian like this. And we won't worry about the normalization anymore. It turns out that in the units we're working in, sigma is a half. So if I use real, so 4 sigma squared is 1. So here, if alpha is real, this is a state that has been displaced in position. If alpha is imaginary, then this is a state that has an e to the ikx in it. It's been displaced in position, in momentum, okay? And so it moves up here instead of over there. So by using a complex number alpha, I can describe where I boosted the vacuum state to in phase space. The real part is the position. The imaginary part of alpha is the momentum. Okay? Is that clear? Yes, sir.
Can you remind us, what is in the vacuum, you just have epsilon and mu?
Yep.
So what, in terms of those, what is the RMS?
Okay, so inside the box, which has some volume, and there's a mode, okay, and I can calculate let's calculate the electric field energy stored in the box. So I have some mode shape and some amplitude. I integrate over the whole volume the e squared over 2 epsilon naught, I guess, and that's some number, to do with the shape of the mode times the square of the amplitude, the e naught in front of there, and that should be 1/2. That's only the electric field, so that should be 1/2 of the 0-point energy, so 1/2 of 1/2 of h bar omega. So the box tells you what omega is, and then you take 1/4 h bar omega, and that tells you what the 0-point electric field is. And it's about 1 microvolt in a millimeter, I think, per millimeter, if I remember right. Okay, so if I just make a coherent state, I just slide up the parabolic potential and let it go, it'll start sloshing back and forth, turning position into negative momentum. That is, it'll start whirling around in phase space roughly 5 billion times per second. It's convenient to go into a rotating frame where it just sits still. Otherwise, it's hard to visualize. Okay, so you can produce these coherent states, these displacements, by just putting a force on the oscillator, just taking an electric field, coming down a coaxial cable and driving the electromagnetic oscillator with a microwave tone. That's classical, okay? But that's the only kind of state you can make. You can displace the vacuum. And you can't make a number state that has exactly 7 photons. You can't make a cat state, and so forth. So we have to learn how to do that using our auxiliary qubit, which I'll show you in a second. Okay, so I showed you that displacement, an imaginary displacement, is a momentum boost, and that's done by this operator. There's a 2 here because of the funny units I'm using. So e to the 2ikx, if you multiply a wave function by e to the ikx, you boost the momentum, right? And less obviously, if you exponentiate the position operator, you displace the position. And to see why that's true, I want to produce this displaced state where delta is some real number. Well, let's do a Taylor series expansion. I have psi naught minus delta, the derivative of psi, delta squared over 2, second derivative, third derivative. And that series of derivatives, because the momentum operator is minus I ddx, when you expand this exponential, it exactly produces this Taylor series. So exponential of position boosts the momentum. Exponential of momentum boosts the position. Is that clear? Momentum is the generator of position changes and vice versa. Okay. All right. So we can't do anything except make those states. So we're gonna, and we're not gonna. Yesterday I talked about this whole network of things, but we're going to focus on one resonator and one qubit dispersively coupled to it, and we're going to use that qubit to help us make things other than coherent states. All right, so just remind you about controlling qubits. A qubit is just some system that has 2 levels. Somehow you can focus on 2 levels, usually the lowest 2, but not always. And there's some energy gap or something that allows you to just make transitions from here to here and back and not go up there. And then, of course, you can describe the states, the superposition states of 0 and 1 as points on a Bloch sphere with 0 at the North Pole, 1 at the South Pole. Sometimes we say spin up and spin down with this polarization vector. And superposition states are, some arbitrary point on the Bloch sphere. And if I start in state 0, I'm at the North Pole, I can rotate the qubit by applying microwave tone to it at its resonance frequency, and it produces rotations that are described by exponentials of Pauli matrices. And the phase of the drive that I apply determines whether I'm rotating around the x-axis or the y-axis. But once I have those 2 rotations, I can generate, that's all I need to generate the whole arbitrary rotation group, because I can also rotate around the z-axis by combining these, as I will show you Okay, any questions? Whoop. Questions about that? So, okay, what happened? Yeah, all right. So before I showed you just if I wanted to apply drives to the oscillator, all I do is produce these displacements. But now I want to use this dispersive coupling to do something more complicated. And without going into details, it turns out that because the cavity frequency depends on the state of the qubit, it turns out that I can do a momentum boost that depends on the state of the qubit. I can make the momentum change plus k if the spin is pointing up, the qubit, and minus k if the spin is pointing down, where sigma z is now -1. Similarly, I can do displacements of position conditioned on the sign of the qubit. And this, to people who work with ion traps, is very familiar. You can apply spin-dependent forces to the ions and excite the mechanical oscillations. Here we're exciting electromagnetic oscillations. And it took us a while to figure out, it turns out it's very simple, but it took us a while to figure out how to go from this and just turn it into this. But it's you have to echo away some terms that you don't want, and then it works extremely well. Yes? It's just the ancilla qubit, yeah. And I'm going to be focusing on using it as a tool just to control the oscillator. In general, you want to control both, but we're going to focus on controlling the oscillator. So, okay, so now we're going to try to make a cat state, a cat first. So here's the phase-space picture of the oscillator. And I'm going to put the qubit into the plus x state, pointing in the x direction on the Bloch sphere, which is an equal superposition of being at the North Pole and the South Pole. Kind of confusing. But this is this plus this. And now I'm going to apply not this, but this qubit-controlled displacement. And since this is a superposition of up and down, the up part gets displaced over to here, a positive amount, and the down part gets displaced over there in the opposite direction. Okay? So this is now an entangled state between the position of the oscillator and the state of the spin. This is a Schrödinger cat. So the cat is alive because it's breathing healthy positive amplitude electric field, and the cat is dead because it's breathing negative amplitude electric field, which is poison. Okay? And so that's a cat, but in quantum optics, people talk about cat states, which is something slightly different, in which you disentangle the qubit from this, and you just end up with the cavity being in two positions, and the qubit is back in the ground state. That's a cat state instead of a cat. It's kind of confusing. Okay, so how do we do that? So we started with, I just showed you, we start with the cavity in the vacuum. We put the qubit in x. We apply this z conditional displacement, and we end up with this entangled state. How do we disentangle the qubit from the cavity? Okay, so here it is. Here's the entangled state. So how could I fix that? Well, if somehow I had a magic ability to rotate the qubit around so this is the x-axis, z-axis, the y-axis is into the board. If I could rotate this qubit around the y-axis by plus pi over 2 so that it's pointing to the right, and if I could take, when the position of the oscillator is negative, I could rotate this guy by minus pi over 2 around the y-axis, then the qubit would always be pointing in the plus x direction. It would be disentangled. Okay? Does that make sense?
Where did you get this out? how did you generate that operator?
This? Oh, well, it's because, yeah, it's because, I don't know what's going on here. The dispersive coupling says that the frequency of the cavity depends on the state of the qubit. So one way to, this is not exactly how it works, but suppose, the cavity has two different frequencies. So I apply a tone with one phase to displace it to the right at one frequency and displace it to the left at the other frequency. It's more complicated than that, but that's roughly the idea. Okay.
But it's, that A dagger A is not X.
Okay, all right. So so let me displace the oscillator. By some real alpha. Okay, and then let me expand this out. It would be if, but alpha is real. Yeah. Okay, actually, okay.
Sorry.
All right. No, it's fine. It's fine. So let me make it. Where now alpha is real, but there's an I. Okay. So then I can expand this out. I get this. Then I get plus I alpha A dagger minus I alpha A dagger minus A, which is the same thing as times, and then I have plus alpha squared times sigma z. Okay? That's the same thing I had before. I got to get rid of that. But look at this. This is the momentum operator times sigma z. Just what I want. Okay? This is a constant Stark shift on the qubit. We can fix that. So that almost works. But there's this original term that I got to get rid of. So what I do is I do one pulse, then I flip the sign of alpha and flip the qubit. And that echoes away this part, but alpha times sigma z is always the same sign, and it reinforces this part. That's how it's done. Okay. That's called the echo control displacement sequence. And it was developed in Michel Deveray's lab. Okay, so how do we disentangle the spin or the qubit from the cavity and have it just pointing to the spin is pointing to the right and the cavity is in a superposition of two positions at once, alpha. Okay? There's something, maybe it's the low humidity, it's causing static, I don't know. Okay, so what I want to do is rotate the spin by plus pi over 2 around the y-axis if the oscillator has a positive position, and minus pi over 2 if the oscillator has a negative position. How do I do that? Well, weirdly, it's to apply a momentum boost. So I want to boost the momentum conditioned on sigma y. If sigma y is plus 1, I increase the momentum by k. If it's minus 1, I decrease the momentum by k. Why in the world does that do the job? Well, you can reinterpret this, and you say, oh, wait, this is a rotation of the qubit around the y-axis by an angle minus 2k times the position of the oscillator. Right? Because this is the thing that moves you around the black sphere. So what I really want is, a rotation as a function of position that's a step function. But I don't have that. But at least I have something which is linear in position. So I adjust this k so that when I get out to my position alpha out here, it's plus pi over 2. And over here in the center, it's minus pi over 2. So it almost does exactly what I want. Right in the center of the peak of the probability distribution, this arrow is pointing exactly in the x direction, and this one's pointing exactly in the x direction. But for larger x, I rotate through a bigger angle. And so it over-rotates. And for smaller x, it under-rotates. And the same thing on this side. So I have a little bit of residual entanglement between the spin and the oscillator position. But mostly it's gone. OK? Is that clear? This is the key step. OK. So and it's really bad over here, but there's almost no probability of finding the particle there, the oscillator there. So it's OK, right? So the vacuum fluctuations have a fixed variance of 1/4 in these units. And so if I make alpha really big, and the rate of rotation is inversely proportional to alpha, then there's very little under and over rotation within the span of the position uncertainty. And as a result, if you calculate the fidelity of this to the desired state where the spin is completely in the x direction, it's 1 minus a small correction that goes away for large alpha. Okay? So it's pretty good. Okay, so can we do better? Yes, and the secret to success is stealing good ideas from other fields. And in 1994, this guy, Wim Paris, who was doing nuclear magnetic resonance experiments, and you have a kilowatt amplifier, and you're sending this giant microwave pulse into this coil to make an oscillating magnetic field to turn over some nuclear spins by pi over 2. And a kilowatt amplifier is a big thing, and it's got diodes, and it's got temperature dependence of the resistance in the coil and gain fluctuations. And so it's very hard to get a very precise pi over 2 fluctuation. Sometimes the magnetic field you apply is too high, and sometimes it's too low. But those are, of course, classical fluctuations. And he invented this pulse sequence. Instead of just doing this, okay, you do this, then you go around some other axis, you do some strange pi rotation, then another axis, a 2 pi rotation, and then back to the first axis, the pi rotation. And it ends up that those 3 extra rotations, if each of them has slightly over-rotates, let's say, if the gain is constant during this very brief interval, then the slight error you made on the first pulse is canceled by the remaining 3 pulses to a very good approximation. And so we're going to steal that idea and use it in a quantum context where the fluctuations and the rotation angle is a quantum operator, the position of the oscillator, and it has quantum uncertainty, right? Just this Gaussian packet has position fluctuations. And despite the fact that this was invented for classical to make classical pulses robust, it works for these quantum pulses. Okay, so here's the, I'm going to define a rotation by angle theta around an axis on the Bloch sphere on the equator, defined by an angle phi, which is how far you are away from the x-axis. So when phi is 0, this is a rotation around the x-axis. When phi is pi over 2, this vanishes, and it's a rotation around the y-axis. Is that clear? And so all the rotations are going to be around some axis in the equator. So here's the original rotation, which I hoped was a pi over 2 rotation. Let's say before I was talking about the y-axis, but now I'm going to use the x-axis. But it's actually slightly erroneous. There was a gain fluctuation in my classical amplifier or something, and it changed the gain from 1 to 1 plus epsilon. So I over-rotate if epsilon's positive. Now I do 3 more erroneous rotations by 2 theta, 4 theta, 2 theta around 2 different axes. And these things combine miraculously because of the way, you do parallel transport on the curved surface of the black sphere. They combine to exactly cancel the epsilon error in this guy. It's amazing. Yeah, the assumption is that the gain is fluctuating over time slowly as the room temperature changes and stuff. But this whole thing lasts a very short length of time. You assume epsilon is constant. That's correct. If it's fluctuating faster than that, then you have to use various echo techniques and things. Okay, so this is called the BB190 pulse that Wim Paris invented because it's a particular broadband one. It's a particular sequence he chose, and it's designed to do a 90-degree rotation. So if you put in an angle theta epsilon here, which you see on this axis 2 theta over pi. So right there is pi over 2. And you look at how much rotation this actually produces by calculating the sign of the rotation. You're changing, this process changes theta epsilon into some function of theta epsilon. And here's the sign of that function. It's very flat top. Okay? So any rotation near pi over 2 will produce very, very close to pi over 2, and the errors will be canceled. Okay? And these are all classical errors, from amplifier gain and stuff. And there's some particular formula for what these other angles are and so forth. And you can kind of see, suppose epsilon is 0, so this is exactly pi over 2. Then this will be exactly pi. That'll be exactly 2 pi, which is the identity. And then there's another pi around the same axis. So this whole thing is the identity when there's no error. That's good. And then it's harder to see, but when there is an error, it corrects that error to the remaining error is 3rd order in epsilon. Okay, so it's great. Now, how can we use that in the quantum context? Because now we have not classical fluctuations, but quantum fluctuations. But all of those pulses are now going to be theta, 2 theta, 4 theta. They're all going to just involve one operator, x, so they all commute with each other. And it's the same as classical physics. So if you're sitting at this position, you will be at that position during all 4 pulses. That's like the gain, not changing. Or you might be sitting at this position. And each one of those positions, then, there's a different error. But through the robust pulse sequence, they all produce a pi over 2 rotation and almost perfectly disentangle the spin from the oscillator. And so it's just literally translated from the classical literature because, yes, these are quantum rotation angles, but they all commute with each other. And so here's, the infidelity. This is the without BB190. This is with BB190. And you can see substantial improvement. Okay. But can we do better? Oh, yes, go ahead. Yeah, so there are many, there's whole families of different sequences. And this is the one for our purposes where we knew we had a kind of Gaussian uncertainty and of a certain bounded width. BB190 has sort of the flattest top response. Yeah, but you can design, for example, these pulses are designed to make you insensitive to small errors. People building quantum sensors who want to find small signals can make other pulse sequences which dramatically enhance the sensitivity because they change rapidly as a function of epsilon. So that's a whole, you can turn this around and use it for quantum sensing. Here we're intentionally trying to not sense the quantum fluctuations. Okay, So can we do better? Well, there's something we haven't used. We haven't used the fact that we can also do conditional displacements, not just conditional momentum boosts. And so we can make rotations by angles that are either quantum variables x or quantum variable p, and those rotation angles don't commute with each other. So this is what we call non-abelian quantum signal processing. Previous example, BB190, was abelian quantum signal processing because all the angles commuted with each other. And it turns out you can use this to great advantage, particularly when you know that the uncertainty actually has a Gaussian distribution. And so you can replace those three rather large rotations in the BB190 sequence with one single rotation with an angle which is momentum instead of position. And it's a very small rotation angle, pi over 2 alpha, small for large alpha. And the reason it works is that when you have a Gaussian and you take a derivative of it, you get something linear in position. And you can adjust that to cancel this linear under and over rotation. And so this much shorter sequence, shorter circuit depth, shorter time duration thing works essentially as well as BB190, and it replaces all these large momentum boosts with one small displacement. And so this is an example, it's some hint. We don't have a full theory of how to do robust control using these non-commuting angles. But this is a first hint, a first application that this is a kind of powerful generalization of quantum signal processing. And so my student Shraddha Singh just defended her thesis, has 3 or 4 other examples used in GKP quantum error correcting codes and so forth. But we still don't have a full theory. So here's as far as I know, the current world record for making Schrödinger cats, not by a slightly different method than I described here. This is Serge Rosenblum, who was a postdoc with Rob Shulkoff, now at the Weizmann. And he's made a cat where the distance between the 2 blobs corresponds to, you usually measure the square of that distance, that corresponds to 1,024 photons. And here is a plot. This is from an earlier experiment in 2013 from Rob's group, where they went up to about 100 photons. And you see this is the Wigner function, and that's a kind of quasi-probability distribution in phase space. It's not always positive because of quantum interference effects. So here's the cat. You have some large amplitude to be at this position, another large amplitude to be at this position. And then you see in the Wigner function these funny interference fringes. They are literally exactly the 2-slit interference pattern between 2 Gaussian slits with that separation. And you can see they rapidly change sign here through here. This is useful for metrology if you wanted to sense tiny displacements that are much smaller than the 0-point position fluctuations. This is the way to do it. And this proves that this is not a mixture of plus alpha and minus alpha position. It's a coherent superposition. And people with ion traps have made, I don't know what the record size is, but I think Jonathan Holm, at least I've seen his data, can make several hundred or maybe even 1,000 size cats. Okay, yeah. Oh, sorry. Yeah, so quantum signal processing is a phrase coined by Ike Chuang, and it refers to taking these ideas from NMR robust pulse sequences. You have some fixed unitary that you know how to do, like an approximate pi/2 rotation, and you get to use that over and over again, interleaved with some other variable rotations to produce these composite pulses. And they have a beautiful review article in a tutorial article in PRX Quantum where they show that almost all known algorithms, Grover search, many other algorithms, can be described entirely in terms of this robust pulse sequence thing, which he coined quantum signal processing. Well, it's a sequence of many pulses, but yeah. Well, there were the original pulse and then 3 correction pulses, yeah.
Well, what's the quantum part? I mean, like, if I had a classical system with non-abelian rotations available, that I apply the same logic.
You could argue that that's what's going on in NMR, where you have a classical spin, which is the gross magnetization. That's right. So, but I called it quantum signal processing because he was going to apply it to small numbers of qubits and create effectively algorithms. So you could call what we're doing quantum signal processing because now the rotation angles are quantum.
Right.
But we decided to call it non-abelian instead. Okay. Yeah. Oh, yes. Sorry. Other questions? Yeah. This is not the largest one they produced. Sorry. Yeah. But in the same paper, this is Vlastakis. Yeah. This is there's up to 100 and something, 110 photons or something. Yeah. I tried to get them to do 137, but they stopped. Okay. So you can use extensions of these ideas to produce other exotic states. Here's a simple example of a squeeze state, and this is this is data from a phase space plot of not the Wigner function, but the characteristic function, which is almost the same thing. And you can see with your eye, those are vacuum fluctuations in position and momentum, and you can see they're squeezed by nearly 11 dB, so the position uncertainty is much smaller, and the momentum uncertainty is much bigger. These are a binomial code quantum error correction word states, a superposition of 0 plus 4 photons. You can see it has 4-fold rotational symmetry as a result. This is this state, which is 0 plus square root of 2 plus 4, square root of 2 plus 4. And this is some other combination. And then this is the state that holds the, until the recent Google 105 qubit experiment tied it, the record for quantum error correction gain. This is the Gottesman-Kitaev-Preskal code word. It's like a cat state in 35 places in phase space at once. And each one of these is squeezed in both directions, x and p, which sounds like that's impossible. But now there are many dots, so that gives you back the position uncertainty. So these are very useful control techniques. Here's the gang that in the C2QA collaboration that we worked on to do this. And here are references. Thanks. So all those rotations were conditional momentum boosts, and we replaced 3 of them with a conditional displacement.